Okay, so our goal, like I said before, our goal for today is really just to do calculations for a weak acid strong base titration. So we're going to use the same concentrations as we did for our strong acid strong base titration that we did last time, except we're going to have a different acid. So the acid that we have this time is propanoic acid with a pKa of 4.86. Okay, and so we're going to go from there and basically just calculate at each of the different points in this particular titration. And there's an added point. So when we did the strong acid, strong base, we had 4 different times in particular that we looked at it. Here we're going to have, as you can see, 5. So we're still going to do the same initial point. Okay, so the initial point here, we're still going to do the pH before the equivalence point, but we're going to do a second version of a pH before the equivalence point, and that's at exactly halfway to the equivalence point. And so that's going to be one of those things that is a little bit different for a weak acid strong base titration or a weak base strong acid titration, because when you get to halfway to the equivalence point, there's a special thing there to make it a whole heck of a lot easier for us to calculate our pH. Then we'll look at the equivalence point again, right? And then again after the equivalence point. And that's essentially, after the equivalence point is essentially the same as it is for a strong acid, strong base titration. So let's get started. So initially, if we look at the pH of a solution of propanoic acid, and we have 50 milliliters of that solution, and it's 0.1 molar. And before we add any base, essentially all we have is the solution of propanoic acid with that 0.1 molar concentration. So we don't really care about the volume initially, because essentially what we have here is just a weak acid solution. And so we have a few things that we need to do for our weak acid solution. So we're given the pKa. Since the pKa is 4.86, we can really easily calculate our Ka. So Ka will just be 10 to the negative 4.86. And that's a good way to start out with some of these. It's an A there, okay. And so you get a value of 1.38 or 1.4 times 10 to the minus 5, okay? The other thing to do here to start out is, as always, is to write out the chemical equation and the expression for the equilibrium constant and the icebox for this, since it is just a weak acid dissolved in water. So we're going to start out with our chemical equation. So we've got propanoic acid, C2H, should be H5, right, COOH. So there's a discrepancy here. So you'll notice those are wrong on this. Forgot to correct it throughout. C2H5COOH. Aqueous plus H2O, liquid, reacts to form hydronium, aqueous plus propanoate, C2H5COO minus aqueous. Okay, and so we'll just start in with this icebox here. Initial change and at equilibrium. We don't worry about the water still. And our initial concentration of the propanoic acid is 0.1000 molar. Okay. We're going to make the assumption here, so I'll just write it in now, and we'll talk about the assumption in a second, but that we have no hydronium, right? That's going to be our concentration of hydronium from the autoionization of water is essentially 0. And when you look at the concentration of the propanoic acid at 0.1 molar, that's much, much larger than the 1 times 10 to the minus 7 concentration, molar concentration of hydronium from autoionization of water. And before the reaction occurs, we've got 0 of the propanoate. So for every propanoic acid that dissociates, we get a minus X. So at equilibrium, we have 0.1000 minus X. We get plus X for every one of those that dissociates. We get a hydronium, and we get a propanoate. So plus X for both of them, which gives us X and X at equilibrium. Okay, and so our Ka expression is the hydronium ion concentration times the propanoate concentration at equilibrium. Oops, COO minus over the propanoic acid concentration. Okay, and that we know is equal to 1.4 times 10 to the minus 5. And as far as assumptions go, since we're almost ready to calculate this, we're going to just write the assumptions on this page, and then we'll do the rest of the calculations on the next page here. So the assumptions are the 5% rule, right? Remember, the 5% rule says that X is less than 5% of the initial concentration of the acid. And the other one is our concentration of hydronium from water is going to be much less than the concentration of hydronium from the propanoate. Okay. And so we'll take this data onto our next page, okay, and we'll start to fill in, we'll utilize our Ka expression, just like we always would with a weak acid in water. And so here we just say, okay, well, our 1.4 times 10 to the minus 5 is going to equal the concentration of hydronium times the concentration of the propanoate, so X and X, so we're going to put that X squared up in the numerator, divided by the initial concentration of the propanoic acid without the X, because our 5% rule says we don't need to do that, okay? So on this, we can solve for X squared pretty easily, right? X squared will equal 1.4 times 10 to the minus 6, which means our X will equal, just take the square root of that, 1.18, really 1.2 if we're doing sig figs, but 1.18 times 10 to the minus 3. And so we're going to say that that's equal to our hydronium ion concentration. And in order to be able to say that realistically, we need to check our assumptions. Okay, and so we're going to check first our 5% rule. And to do that, we just take the concentration, so basically take X over the initial concentration of the acid, so 1.18 times 10 to the minus 3 divided by 0.1000 times 100%, which gives us a value of 1.18%, and so that checks out, it's less than 5%. The other one we're going to check, right, is the concentration of hydronium from water being less than the concentration of hydronium from the propanoic acid. Oops, C8, there should be a 5. C2H5COOH. There we go. So on that one, we just take the 1 times 10 to the minus 7 molar concentration of hydronium from water, divide that by the 1.18 times 10 to the minus 3, times 100%, and we get a value of 8.5 times 10 to the minus 3%, right? And so that one also checks out, which means we can just go and plug that value that we got up here, right, in for our hydronium ion concentration, noting that we have 2 sig figs here. So we can say pH is equal to negative log of 1.18 times 10 to the minus 3, right? With we'll have 2 significant figures after the decimal in the mantissa, and we wind up getting a value of 2.07 for our pH. Okay, so far nothing has changed from what we've done in the past. That's still just a weak acid in water that we're calculating there. Okay, so that's the starting point in that titration. All right, any questions before we move on? All right, if you have those questions, leap in and ask. The next point we're going to look at is before the equivalence point. And like I said, we're going to look at 2 different times before the equivalent point. Here, we're going to look at 10 milliliters of base added, okay? And so what we need to know here is, first off, how many moles of acid we began with. So initial moles of acid. So that's as simple as just the concentration times the volume. So 0.0500 liters times the concentration of 0.1000 moles per liter. So we started out with 0.00500 moles of acid. Okay, so that was our initial number of moles of that weak acid in solution. The next thing we want to do is, again, so this is really similar to how we started our strong acid, strong base titration, because we also want to figure out how many moles of base we added. Okay, and so for this one, right, we're going to just take the volume of the base, so 0.010 liters, that's our 10 milliliters, times the concentration, 0.1000 moles of sodium hydroxide per liter, gives us 0.00100 moles. Actually, should just be, let's see, 10.0, so I need another 0 in there. There we go. Moles of sodium hydroxide, okay, that we added, okay? Now, because of the reaction between the sodium hydroxide and the propanoic acid, namely the C2H5COOH plus NaOH, what's going on there is we're making now, because the hydroxide will deprotonate that acid, we're making sodium propanoate, C2H5COONA plus H2O. So we make that water. So essentially what we did here is we turned a weak acid into its conjugate base. And so the way we figure out how much of that conjugate base is actually, it's just tied to the sodium hydroxide. Notice the sodium hydroxide here is, if you will, is a limiting reactant in this particular reaction, right? We had 0.00500 moles of that, and we had 0.00100 moles of the base, which means we can only produce that many moles of the conjugate base, okay? So we make here, we make here 0.00100 moles of essentially this propanoate, which is the important part, right? C2H5COO minus. And we have left, right, remaining, we have 0.00400 moles of the C2H5COOH, right? So we'll take those values onto our next page. Now, something you can note here is you can go and find the concentration, but one of the things that we talked about briefly last time is that when you know the moles of each, you can actually just plug these into your Henderson-Hasselbalch equation, because at this point we have a mixture of a weak acid and its conjugate base, which means this solution is a buffer, right? And so to calculate the pH of a buffer solution, we use our Henderson-Hasselbalch equation, right? So we use that Henderson-Hasselbalch equation for this. So we know that the pH is equal to the pKa plus the log of the concentration of the base, the conjugate base, so A minus, just generically, over the concentration of the acid, HA. Okay. And so here, we just plug these in. Our pKa was given to us at 4.86 plus log of 0.00100 over 0.00400. And again, remember, we can use just the moles because the volumes will cancel out because they're both in the same solution. And so in this calculation, you wind up getting that the pH will equal 4.86 minus 0.60. So you wind up with a pH equal to 4.26. So anytime that you're between the beginning point before you add anything and the equivalence point, any of those times basically you can utilize this Henderson-Hasselbalch equation to calculate the pH, because the solution is a buffer as soon as you start to add the base, because the strong base just deprotonates the acid. Okay, so it makes a buffer solution. Which, by the way, if we go back up to our that beginning stage here, you know, notice here how the pH increases slowly when you start. Well, as you add that base in, you turn it into a buffer, right? So you turn it into this buffer, and it's a buffer solution until essentially you get past or near the equivalence point. So the pH is going to change very little in that time as you add the strong acid, as you add the strong base to the acid, because that strong base is just reacting with the weak acid to turn it into its conjugate base, right? It's not really contributing so much to the hydroxide ion concentration. It's more so just deprotonating that weak acid, right? And so I told you we'd look at one other point in this particular titration beyond what we did in the strong acid, strong base titration, and that's at 25 milliliters of base added for this example. This is halfway to the equivalence point, right? So halfway to the equivalence point is a useful thing for us to just look at from the standpoint of the math of it. So what we know right now is that we started out, right, with an initial acid amount of 0.0050, that didn't write very well, 0.00500 moles of this propanoate, or excuse me, propanoic acid, okay? At this point, let's just check to make sure we're at halfway to the equivalence point. And so we want to see how much of the base we've added. So we can look at the sodium hydroxide added. Okay. When we look at that, we can see that, well, we've added 0.025 liters of 0.1000 molar sodium hydroxide, which is 0.0250 moles of NaOH. Okay, so in other words, we've turned, right? We've turned I lost a zero in there, 0.00250 moles of sodium hydroxide. We've turned that many moles, right, of sodium hydroxide into the propanoate. And that means we also have that 0.00500 moles of propanoic acid minus the 0.00250 moles of propanoate. Excuse me, what did I do here? I said something and I didn't write it right. That should be a minus on there. So we have 0.00250 moles of propanoate. That propanoate that we've made comes from the propanoic acid that's been deprotonated. And so we're left with 0.00250 moles of propanoic acid, C2H5COOH. Right, so we have now our acid, that much acid, and we have this much of its conjugate base. And so this is still now a buffered solution, right? But now our buffered solution has equal amounts of both the conjugate acid and its conjugate base. Okay. And so when we put that into the Henderson-Hasselbalch, we get pH is equal to pKa, so 4.86, plus log of 0.00250 over 0.00250. Try to make that a little, oop, that didn't work, eraser, there. Right? And so essentially this whole piece, because you have essentially the log of 1, if you do the math on that, that piece, log of 1 equals 0, and so your pH is going to equal 4.86. And that means your pH is equal to your pKa at halfway to the equivalence point. Okay, that's why that one was added in here. Is I wanted you guys to see that is if you notice that you're halfway to the equivalence point of a titration, you can determine the pH just by having the pKa. Also, if you happen to go to the full equivalence point, right? If you get to the equivalence point, you can say, I know the added volume at the equivalence point. And so if I look at the pH at that, at halfway to that, so if I add 20 milliliters to get to the equivalence point, I can look at the pH at 10 milliliters, and that pH is equal to the pKa for that acid, right? So if you know the pKa, you know the Ka because you just plug it into the equation. 10 to the negative pKa gives you the Ka for the acid. So that's how you can easily figure out the equilibrium constant for a weak acid. You just do a titration, you look at the pH at halfway to the equivalence point, voila, you're done. Okay. All right, so that's the third step out of these 5 that we're going to do. Any questions so far? All right, then what we'll do is we'll move right along to the equivalence point. So at the equivalence point, right, we have added now 50 milliliters of the acid of the equal concentration, 50 milliliters of the base to the equal concentration and volume of the acid. So we have now added equal moles of both of these substances. And so once we've added the equal moles, we've essentially deprotonated all of the acid. So all of the acid is converted to its conjugate base. Okay. At this stage, we now have a solution, right? If it's converted to its conjugate base, well, the conjugate base of a weak acid is a weak base. So we have a solution of weak base, right? And so if we have a solution of weak base, we just do the icebox. We do that whole calculation that you do for a weak base in water. And you figure out the pOH, and then from the pOH, you can figure out the pH. So we'll go through that as well, okay? And so what we can do now is we can see, well, what we have to do here to begin with is figure out what is the concentration of the propanoic acid that remains. So the C2H5COO minus, so that propanoate that remains, that concentration will be, well, the initial number of moles of the propanoic acid, because all of those moles are converted to the conjugate base, so 0.00500 moles of C2H5COO minus over our new volume. So our new volume is the initial 50 milliliters, or 0.0500 liters, plus the added 0.0500 liters. And so we wind up with a concentration of the common ion of that propanoate of 0.0500 molar. Okay, and so that's going to be our initial concentration for our icebox as we go through this reaction. So I'll start setting up the icebox on the next page. So here we have the propanoate, C2H5COO minus aqueous plus H2O liquid, reacts to form the protonated version, so this the propanoic acid, to C2H5COOH plus hydroxide. And so we've got our initial, the change, and at equilibrium. Ooh. There we go. Okay, and we can fill in our icebox much the same way. Here, 0.05 molar was our initial concentration, minus X, so at equilibrium, we've got 0.0500 minus X. Start out with none of that. We're going to make the assumption that the concentration of hydroxide is small from the autoionization of water. And so we're going to leave that as a 0. So we're going to get plus X and plus X. Okay, so we have X and X. The other thing we need to do here is we need to calculate our Kb. So we know that the Ka is 4.86. So we can calculate, pKa is 4.86. So pKb will equal 14 minus the pKa, so 4.86. And so we get a value of 9.14, which means our Kb is 10 to the negative 9.14, which will give us a value for our Kb of 7.2 times 10 to the minus 10 value. We also know our Kb is equal to the concentration of hydroxide times the concentration of the propanoic acid divided by the concentration of the propanoate, the deprotonated. And so that will equal, just as a note, we're going to use our assumptions. Okay, the 5% rule and the concentration of hydroxide this time from water is much less than the concentration of hydroxide from the propanoate. Okay, did I give myself another page? I didn't, so I'm going to go in and give myself another page for this calculation. So 1 second. Let's add another.
Professor?
Yeah.
I'm sorry, would you mind going to the previous slide real quick?
Yeah, 1 second. So the one before this one here?
Yes, please. Thank you.
Mm-hmm.
All right, thanks. Just wanted a screenshot of it, so thank you.
Gotcha. Okay, so we're at a point now where basically we have these assumptions that we're making, right? The assumptions being the same type of assumptions that we've done in the past. So, so we can plug in the values for the concentrations at equilibrium. What the heck? Nope. Apparently my pen is not there. Okay, try this again. There we go. Okay, so we can plug those values into our equilibrium constant expression. We'll do that on the next page. So we have our KB, which is 7.2 times 10 minus 10 is equal to x squared over 0.0500. Squared will be 3.6 times 10 to the minus 11. Okay. And then we can take and say x should equal 6 times 10 to the minus 6. And so since we have a value, this is going to be a fairly close value for our concentration of hydronium from water, but for the 5% rule, as we check these assumptions, it's not very close. All right, so 5% rule, right, we've got 6 times 10 to the minus 6 divided by 0.0500 times 100%. That gives us a value of 0.012%. So the 5% rule checks out. Concentration of hydroxide from water, that one being much smaller than the concentration of hydroxide from the weak base. Okay, so for that one, we take and divide, so 1 times 10 to the minus 7 over 6 times 10 to the minus 6. We wind up getting, times 100%. Okay, we wind up getting a value of 1.67%. Okay. And so that 1.67% is less than 5%. So that checks out. And so we can now take and say, well, our POH is equal to negative log of 6 times 10 to the minus 6, which is 5.22. And so our pH is equal to 14 minus 5.22. And so we get a pH of 8.78. Okay. So this is now at the equivalence point of a weak acid strong base titration. You are left with just the conjugate base. And so it's just a solution of the weak base that is the conjugate base of that weak acid. Okay. All right. So we've got one more to do. And this one is just like the strong acid, strong base titration. We'll sort of talk a little bit about why as well. So we're going to calculate the pH at the the last stage for us is after we've added beyond the equivalence point. And so in this case, 75 mils of base will have been added. And so we still have initially, right, we had that 0.00500 moles of the acid. Okay, we have now added more base, right, than acid. And so the amount of base added will be, well, the 0.075 liters, so 75 mils, times 0.1000 moles of sodium hydroxide per liter, which gives us 0.007500 moles of NaOH. Okay, and so we can look and find the excess sodium hydroxide. Okay, and so that's going to be the amount of sodium hydroxide that you've added. So 0.007500 moles. So I think I have too many zeros on there. So moles of sodium hydroxide minus the initial moles of acid. Okay. Okay, so you have, in this case, 0.00250 moles of sodium hydroxide, okay, or how much of the strong base you access. But you've also turned all of that weak acid into its conjugate base. And so you actually wind up with 0.00500 moles of the conjugate base, C2H5COO minus, okay? So you have these two bases in solution. And the key here is the strong base is the one that's important for the concentration of the hydroxide, right? Basically, the weak base that you have over here is going to add very, very much insignificantly to the amount of hydroxide in solution. So you only have to worry about the excess amount of the sodium hydroxide in this reaction, okay? And so we have 0.00250 moles of sodium hydroxide over the total volume. So the initial 50 milliliters, 0.0500 liters, plus the added 75 milliliters, 0.0750 liters, gives us our concentration of the sodium hydroxide after the reaction, right? And so this comes out to be 0.167 molar NaOH, okay? So there's our concentration of the sodium hydroxide. And so it's a sodium hydroxide solution. Oh, I lost a zero here. There should be 0.0167, excuse me. So to find our pOH, since it's a strong base solution, essentially, we can say our pOH will equal the negative log of the concentration of sodium hydroxide, which will equal negative log of 0.0167, and the math works out to give us a value of 1.78. So our pH will equal 14 minus 1.78 to give us a pH of 12.22 after the extra 25 milliliters of base has been added. Okay, and that takes care of our titrations of a weak acid with a strong base. Okay, and so we'll end there for today. What we'll do next time, we've got a little bit left. We're going to talk briefly about a weak base strong acid titration and some polyprotic acid titrations and indicators before we move along to talking about ion solubility in the next chapter. Okay. So with that, I'm going to pause or stop our recording.